So welcome to the Neural Ace podcast, episode 3, with Eric Matzner.
Matzner. Happy to be here.
Happy to have you on the podcast, Eric. So Eric recently gave a talk on neurogenesis, which was fascinating and eye-opening. And while he was giving the talk, we had a peek at his computer, and he had countless documents he studies the brain. It's pretty obvious. Countless research documents into how neurogenesis works. I mean, just the unbelievable amount of files. I've never seen that many files.
That was just my desktop, I think you guys saw.
So this man studies the brain, and when you study the brain, you're a neuroscientist. So when I found out that I would have the chance to talk to him for the podcast, I jumped at it, because that's what he does.
To be clear, I'm not a classically trained neuroscientist, but I definitely think I spend more time researching the brain than most neuroscientists, like scientists and doctors. I pretty much am, through my business of running a nootropics company, Nutro, I am basically a paid researcher all day long on enhancing the human brain and memory and learning and the growth of neurons, which is what neurogenesis is for those who don't know. And that's something that I try to find a practical application for. Instead of just doing research, I live the research.
Eric Matzner is the CEO of a nootropics company. And we're finding out what is nootropics and how do nootropics interface with Neural Ace. So that's...
If we're using neuroplasticity changes and neurogenesis changes, and since nootropics facilitate neuroplasticity, the change between connections in neurons, it might facilitate the integration of these devices. I actually was in discussion with a couple doctors, one who's doing some biofeedback things and otherwise, and mentioned to him how these nootropics might offer a way for the body to more easily integrate with these devices that people are trying to learn and use stimulation and muscle stimulation through their devices. You've got like Adam Gazelli has some biofeedback devices, and a couple other people I've been interested in getting into with, but there's honestly not a lot of research in combining nootropics with those activities. There is definitely some research on nootropics plus brain training. Sure. Has a better effect than either alone.
Now, so as a researcher, how far have you dived into like the metabolism of neurons and glia and how that functions?
I'm interested in the mitochondria a lot, which are making the energy in the brain.
ATP.
ATP, correct. So increased brain activity does use increased mitochondrial activity.
Absolutely.
So that, when you talk about brain nutrition, is kind of a thing that might be required, is to increase your brain's supply of the precursors that are allowing for energy building. You also want to have the phospholipids out there, which are going to help build new cells, including DHA, like it's in fish oil, because the brain might hit a physical limitation on trying to like interact with these machinery, and it may be augmented by these substances. And I've been looking into, I haven't done enough research on them, but I'm starting to look at cochlear implants and other type of implants and see what you can do to like more rapidly integrate those into the brain, because I think there'll be something analogous for when we're looking at neural aces.
So I spoke to David Eagleman on November 19th, and I was it was at an event, and I just he was talking. I don't remember if he was talking there, but I asked him about my hypothesis about how we can send VR directly to the brain. But I was careful about how I phrased it. I said, if we stick all these new sensors in the brain, won't they inhibit the other senses? Similar to how so my idea was, won't a new sensor input regulate the intention gain of the brain and inhibit other senses? And I don't think at that time he was on the same page with me about what would happen, because he talks a lot about, adding new sensors to the brain. So a kind of reverse example that I can show him is that if you put on a blindfold for 90 minutes in total 100% darkness, your visual cortex assumes that you no longer have eyes. and you may start to have like audio hallucinations if you're listening to music or a podcast, and your visual cortex may begin to process what your ears are hearing. So what I'm talking about then with neural lace is that when you reverse that process, if you take even whether it's neural lace or whether it's just, adding in 10 extra eyeballs, that was the correct question I had. If you add in 10 extra eyeballs, you're doing the reverse of wearing a blindfold. And so when you take the blindfold off to your brain, you're now adding in new sensory inputs. And these new sensory inputs inhibit the auditory processing back to the same levels they were at before you put the blindfold on. So if you gave yourself 10 pairs of new eyes, it's going to inhibit some other part of your brain function that operates for your other senses. That's my hypothesis. At the time, I didn't get the chance to get all of that out because we were at an event. But I hope to convince him. Hope to talk to him again about that topic. And yeah, so that's what I was talking about with David Eagleman.
Yeah, I've talked to Eagleman as well. He was one of the people that I actually spoke with him after he was interviewed by Adam Gazzaley. And he didn't actually. I wrote him an email and I sent him all these papers and about mossy fiber reorganization, and things like that, increases in the waves in the brain that are caused by nootropics. I didn't get a response from him, but I think that he probably doesn't necessarily know the answer. But I think that any extra usage of the brain, including 8 more eyes or 10 more eyes, would cause an increase in energy in the brain. Fortunately, the brain is really efficient, but weighing only 2% of our body weight, it uses 20% of our energy. And there is actually limitations evolutionarily on that energy usage, because if you use too much energy before you could get your next meal, you would die. And so I think part of what nootropics do is they allow us to, for example, use more of the neurotransmitter acetylcholine beyond what would be a normally okay level. And so some people, if you don't supplement with acetylcholine or another precursor for acetylcholine, you can get a headache or you can have other issues. So in my pills, we put that in there, but I definitely think that shows that the demand is increased. And also I know about neurotransmitter precursor signaling, where if you have those precursors in there, your body will naturally amp up the production of those downstream neurotransmitters.
So you were just before the talk today, you were showing me this this one researcher. He has this injectable, what is it? Injectable
probe, I guess it's called
sort of a probe, and it's a sensor that you inject, and then it sends a signal outside the brain, or.
It looks like they're going through the brain, through blood vessels, through a vein, to basically try to get in the brain without causing physical damage.
And these are nanomachines, and they're planning to inject rats with them?
I think they got them into some rats. I think we're looking at two different things. One was a guy, I believe he's an Australian researcher who has that probe, and then we were looking at a paper called Injectable Synthetics or something like that, which looks to be pretty amazing if we can get that technology into rats, to human brains, and in the rat brain. I think the brain is difficult in general to go into, because once you're in there, there's a lot of trouble you can cause very easily. And I think that was part of the issue with that guy with the probe, is that they're going through the vessel, so they're not going directly into the brain. They want to pop out inside the brain, kind of use it as a source system and a back level in there. I've seen some other promising technologies. One of them was a friend who says his company was working on, I don't know if it's NDA or not, but basically they inject something in your shoulder and your collarbone, basically near your neck, and then they grow neurons up. They're trying to build a link from that device that sits outside the brain and build a neural pathway up your neck and back into your brain. So that one's kind of an interesting one to me, because they're recognizing that they can't go directly in the brain as easily. Yeah. And they found a way to do it outside and then hook into the brain's network. Yeah. The question I have is, what happens once you program into the brain? What kind of information are you going to be getting? What kind of signal are you going to transduce? Right. Are you going to be able to just come up with a yes or no the device has, and maybe that's enough of a signal? Are you going to be able to wire into some other processing that
there's a lot of different sensors and new ones that I'm learning about every day. There's a lot of companies that have been stealth or just announcing new sensors. So a couple years ago, I saw a sensor that's basically, it's not only a sensor, it's also a transmitter. And so it senses electromagnetic waves and transmit them. There's a number of companies that are building like artificial neurons. In terms of like nootropics and energy demands that we're putting on the brain, and ultimately an artificial neuron to really behave like a real neuron would be able to supply the brain with energy in terms of like in terms of being a proper interface between the brain and not just like feed off the brain or interface like a normal neuron.
Yeah, so that means it would need to have the same similar structure, and it would need to release neurotransmitter chemicals. So
right.
If you're making a hard machine, you're either going to have to keep resupplying those neurotransmitters or have some way that it can what's called endogenously produce. So it either need what it could try to do is potentially tap into the body's system for restoring these neurotransmitters already.
Yep.
And put those in. The question is, could it generate its own new neurotransmitters? So things called neuropeptides, which are short chains of amino acids, they can signal as if a neurotransmitter. In my gold pills, there's something called Nupep, which is a Russian dipeptide form of paracetam. Paracetam being the original nootropic. A dipeptide form being the short chain of amino acids has a much easier way of crossing the blood-brain barrier in the stomach and other ways to the body. But it's considered a neurotransmitter in that way. And there are also hundreds of neurotransmitters. We don't even know all of them, and we don't even know even the limit on how many there are. But realistically, we talk about less than 10.
Yeah.
People know about like serotonin, dopamine, acetylcholine, epinephrine, and I don't know what other people know about. But
I also want to mention that there are biohackers working on creating artificial cells from DNA. So hopefully that means eventually, and it's still like this hasn't happened yet. It's sort of like one of those holy grail moments. Like, can we create an artificial cell? Actually, I don't know. Has it? There was been some recent announcements.
There is somebody who they've made an artificial life form that has its own type of programming. Whether that is relevant in the brain, I don't know. I think we'd be much more able to I think looking at TCDS and sending electrical waves to the brain.
Transcranial direct current stimulation.
Yes. Looking stuff like that where you're physically stimulating the pathways, or they have where they do optogenetics where they put in a light sensitive gene from a jellyfish that when they put light on it directly actually on the brain,
that would require genetically
on
engineering human brain cells and then injecting them into the brain.
Yes, it would involve modifying the brain's DNA. And they're doing. Yeah, go ahead.
So I thought, well, transcranial magnetic stimulation seems like it reaches deep into the brain from remote. The big problem with that, I heard, is that it's actually like trying to interface with the brain with a shotgun. It's too big, but they're currently working on reducing it so it's less like a shotgun and more like a surgical knife.
Yes, they have some that are implants in the brain for people with strokes and other types of ailments that will try to stabilize the brain or fire. We're starting to get pacemakers built into the body that automatically gives your heart a shock if it's needed. So I think that there's things that are making progress, but again, they are definitely shotgun type approaches. The brain is just difficult to experiment in human brains. Even cracking open a human brain is not something you do lightly.
Right.
So I think we really need to figure out methods to do this in animals, and that means from whatever's figured out in animals to humans is 10 to 20 years at the current cycle. Hopefully things speed up. Hopefully we get some...
Well, okay, so what I'm advocating is that we use some new wireless technologies that I know about are coming to the market. I mean, there's a lot of different ways we can go about solving neurowaves, but we should use wireless. For example, let's take the topic of tractography, which is usually associated with MRI and diffusion tensor imaging. The traditional course of tractography is that you do basically an MRI scan from multiple angles, at least 3 different angles, and then you combine the different. You have an X capture and a Y capture and a Z capture, and you combine the different angles. The computer figures out the geometry of all the it's receiving the image capture from different angles, and it's creating an image in 3 dimensions.
That's great if you want to control your computer while sitting inside this giant MRI machine in a hospital. So, like, could you be walking around?
So, little known secret is that tractography is not is more it's tensor calculus. It's not limited to the domain of giant magnetic machines or MRI.
Well, that's good.
So if we can stick multiple sensors in or near, let's say that we stuck, we could do tractography with other kinds of sensors, which is the point I'm making.
Okay.
And that means that you're taking multiple snapshots from different angles of the brain, and then you're using a computer program to stitch together those images and to create a 3D model of that space. Even with, the limits of what you can do with MRI, though, are not really reached. Like currently, MRI, you're getting like the voxel size could contain, like 1,000 neurons, for example, or many more than that. And that's not the definition we're going to need for neural lace. But if you're taking 3,000 images from multiple angles, right, and you're doing tractography with a massive amount of images, and then you're thinking about something from virtual reality, which people may have tried. It's called Photogrammetry, where there's an app on the Vive called realities.io, where you can walk inside a virtual room it's photorealistic, and you can lean around. When I was at CES 2017, I tried this new technology by a company called HypeVR. HypeVR introduced the ability to walk around inside a video. So you're moving inside a video. And at the X-Tech Expo recently, so the PlayStation VR chief, Dr. Richard Marks, showed me a demo of the new Sony technology being developed in the UK, which allows 6 degrees of freedom position tracking at the from a regular 3D 360 video. And actually, Facebook just unveiled some new cameras that at F8 that actually allow, basically they're not going to sell the cameras directly, but it's a hardware spec that allows you to have either an X24 or 24 cameras or 6 cameras in one device. Allows professionals to capture video with 6 degrees of freedom. With both techniques, though, you obviously would have some occlusion depending on how far away you attempt to move from the origin point of the camera. So these are primarily aimed at professionals to record like concerts and movies, plays, live shows, and then the concert itself, or the concert hall, or the producer of the film or of the show would then do a lot of post-production to fix it. So that is the technology coming down the pipeline that allows us to do basically videogrammetry, to move around inside the videos in real time. So the next step then, of course, is to take the core of that videogrammetry process, which is photogrammetry, and apply it to medical imaging. Like a massive...
That new Electro camera looks amazing.
It's massive, and it's super expensive, and it creates that's light field is amazing, but it's also a fire hose of data. So HypeVR has got this advantage where they're using actually just thermal compression, but they're bringing down the size of that data to something you can download on and watch on your Oculus, which is a huge step forward. You gotta compress it, you gotta make it shippable. But now Sony in the UK has come up with a technology where you can take a standard 3D 360 rig, which is so much less expensive, and you can make a movie that you have position tracking. And I was in this concert hall, and I noticed that the reflections just looked a little bit too good. I could lean around corners, the parallax was too good. And this is because when you do photogrammetry from a fixed point of view, you can't see what's around the chair. So the solution, this is going to be an enterprise solution. It's not immediately available to, this is for people who make, it's going to be for people who make concerts to actually, I need to get through this a little bit faster.
Yeah, sorry. But what are they going to do with the technology related to neural laces?
Okay, so the point being is that this technology is coming down the pipeline so fast. What you can do with it, though, is you're turning four-dimensional video, and the computer's figuring out the geometry from four-dimensional video from all these different angles, and it's creating like so this is the technology that we can now apply to medical imaging. So instead of like focusing on the outside world, we turn this around and focus it on the inside world. So we take 3,000 images of the brain with tractography from different, and we're combining it with not photogrammetry, videogrammetry, right? And which is a massive computational problem, but we do that, and now we can track like basically like everything going through a specific region of the brain, or at some point we're going to be able to do the entire brain.
Does this still keep us from? Is it still considered neural lace if it's purely external in the brain?
Well, so the information. Because if it's pure, so we need to do two things with neural lace. One is sense, and one is transmit. So we need a two-way directional information. So for research purposes, that will get us halfway there. Then we need to transmit the stuff back into the brain. That's the other half of it. What I'm saying is that, there's all the. So we have. So what I'm working on is new designs for combining new forms of tractography with technologies like videogrammetry to figure out. Basically, we're getting a lot of new brain data. Then what I want to do is take 12 DGX-1 supercomputers, the NVIDIA supercomputers, that each cost like $129,000. And we're going to take that data and see. There's a lot of brainwave data there's a lot you can do with a supercomputer right now that's not being done. Current EEG has not even reached its potential. Current MRI or DT has not reached its potential, not yet. But I want to take this and I want to do sort of like the self-driving car project, where you are analyzing the biomarkers of the person, their heart rate, their pupil dilation, their eye movement, their body movement, all the medical imaging, their eye and everything.
All biometrics you get.
And then we will need to do the environment too. So the environment is like, Facebook just announced at the F8 today that they have AR product that they're shipping, and AR is computer vision of everything on your table, your cup, your glass, the table itself. It says this is a bag, and now it's made a virtual object of it so that your apps can, with your phone, interact with your table. It recognizes everything around you. So we need this kind of technology, which they're taking from in the supercomputers that goes in the back of your self-driving car, and they're making it work on a little phone, which is just incredible. But we need to categorize the objects in the environment, and then this is what the 12 supercomputers are going to. They're all going to be looking categorizing what's in the environment with what's going on in the brain, and they're making the links between the neural correlates between the object on the table when you're looking at it with the eye tracking and the pupil dilation and how you respond, and then the tractography of your brain and what's happening there in terms of electromagnetic waves or neurotransmitters.
Yeah, I think it's interesting.
And so we're going to figure out what those signals are exactly, and
I think we can start to translate what we're seeing and doing and feeling in the space so that we can let this device that's on us or in us comprehend it. I think that's a starting point. I think as much as you could do outside of the brain to start processing for the neural lace is important. I also think it's possible, like, for example, I have something called the North Paw.
Yeah.
And it's a magnetic, it's a band that goes around your ankle. It has like 8 pager motors, one in each direction, and it has a digital compass, and it constantly vibrates the direction that north is in.
Yep.
And if you wear this for a while, you start to just know, like, it's literally vibrating all the time you have it on. It lasts for like 8 or 9 hours. And so all the time it's on, you know which way north is. And so your brain starts to feel this, and you eventually stop feeling the vibration. You just know which way north is. So it becomes pretty easy to like add in information into the brain, which is something I really believe the brain will function like a USB port. I mean, I met Neil Harbison at a body hacking conference in Austin a year or so ago, And he, Neil Harbison's the first official cyborg. He has a picture with his passport with the device in his head. He's colorblind, and so he actually has a camera in his head that detects color and transmits it into vibration and vibrational signals that correspond to different sounds. And so he's a real synesthetic where he hears color. And so he could look at you, you have a black shirt on, he would know the tone, even without being able to detect it. He could look behind him, and he's actually able to basically feel color in a way and feel a new sensation of how someone lights up, basically, or how they sound from their color. So he's really doing something interesting, and he could tell you what color it is based on the sound, and he has a true innate feeling that is like an add-on into his brain. So I think that our brain has the potential to pretty easily add these things in if we feed it the data. So I think, playing off of what you're saying, if we figure out ways to feed it this data, the device can like maybe understand more without having to do any processing in our brain, and it can then interpret it and signal to us what's going on.
Yeah, and I also want to, I also want to talk about the feedback so neuroscientists, we were talking about before the podcast, neuroscientists are beginning to speak up provide feedback about what they think is possible in terms of neural lace, especially with Neuralink being a big topic. And I've been getting feedback personally, like people are like, well, why would you like give away, don't give the secret sauce away on your podcast, and like, are you devaluing yourself? Like, what's your value proposition if you want to work with a company that's doing neural lace? And so I wanted to maybe bring that into the conversation a little bit, because we're talking about here's the thing is the thing I want to say is there's no secret sauce for neural lace. I could talk all day about all the things we can do in terms of computer imaging, in terms of but that doesn't. But see, Google can give away TensorFlow, and they did. TensorFlow is the deep learning library. But the thing is, it doesn't replace the fact that Google has its own chips. They have their own servers. The servers are massive. They have their own engineers. The engineers themselves are not giving away their value. The value of creating the Neural Lace podcast and talking about all this stuff is that I can reach more people with this podcast who will say, hey, man, that's a great podcast. Here's what I've been working on. And they contact me. And for example, like I reached out to Elon Musk, and I raised a 10 million, GoFundMe. And I'm not relying on that at all. I was like, why not? Why not do it? Some people are like laughing at that. And I'm like, wait, why not? The thing is, what happened was someone called me up the next day. Actually, we're going to talk tomorrow. And the thing is, they're saying, okay, what would you say to Elon Musk and all this stuff? And I said, and then I'm answering, so do you know Elon Musk? He says, no, but I know this other guy. And this other guy wants to do, my impression is this other guy wants to do neural lace. So it turns out it's not just Elon Musk, it's not just Colonel, it's not just me. There are other companies in stealth mode that want to do neural lace, and that's the value of this podcast. And I'm not giving away my value because there is no single secret. I mean, I know my value is not just the libraries in my head, it's also my network. I mean, I know companies that have products that like new sensors that have massive capabilities that I know Elon Musk doesn't know about.
Yeah.
So if companies want to work with me, and we can beat Elon Musk to the punch. That's what I'm saying.
Personally, I would never bet against Elon Musk. I know George Hotz is a friend of mine. I've seen him bet against Elon. That generally doesn't seem to work out well. I also, I'm on a Hyperloop. I'm on a team building the Hyperloop in the Elon Musk competition.
No, I'm a fan. I'm a fan of Elon Musk.
I'm for encouraging the diffusion of these type of technologies because they offer us a way to upgrade ourselves in a serious way. I constantly wish I was a cyborg, or where I could query the internet and get an answer back. That would be probably a whole sea change in terms of learning, because at the moment I struggle with the physical limitations on integrating information into my mind. I read at 1,200 words a minute or so, which is basically at the well beyond the normal.
Nice. Is that photo reading?
I use a form of what's called RSVP, Rapid Serial Visual Presentation, where it puts one word at a time.
Oh, yeah, and I've tried that. It's an app.
It's an algorithm. The company named Spritz kind of redid this algorithm and then got ripped off by everybody.
Nice.
And so you can find generic open source versions of it. Where
if you really, sometimes when I really want to digest a book,
I'll read it the normal way, and then I'll do it also with that app.
I just speed read first. If I really felt like people say that to me all the time. But if you're reading a book and it takes you a month because you're reading it chapter by chapter, I read Ready Player One in like 3 hours. So it's a few 100,000 words. So I was able to take it in.
That really sounds reasonable because actually the audiobook version of Ready Player One is 6 hours.
Okay.
Yeah. So the speed reading in 3 hours is totally reasonable.
Yeah.
Your brain can handle it for sure.
Yeah, so I mean, there is a limitation on like how fast audio processing. I think there is not really a limitation on how fast your eyes can process. If you're able to like form the syntax around it, I kind of use my own sort of synesthesia to do that. But I would love for those words or those thoughts or those ideas to pop into my head.
So one of the ideas David Eagleman talks about, he says if you put a blindfold over your eyes for 90 minutes straight, what happens is your visual cortex, which takes up 2/3 of your brain activity, which may be part of why your eyes process stuff faster, 2/3 of your brain is doing your visual stuff. If you cut that off for 90 minutes, like total blackness, not a single speck of light, your visual cortex will then start to process other stimuli that's coming into your brain, like from your ears, for example, or from vibrations.
Well, light is the fastest traveling thing we know.
Sure.
And so the neurons in the brain actually fire much slower than the speed of light. But the idea, though, is that eyes evolve in nature because it's the fastest signaling, and whoever's the fastest is going to survive that interaction. So you have multiple development of eyes throughout.
But what's interesting, though, if you're listening to an audiobook after you turned off your visual cortex, then you start to visualize the audiobook. And so now you have your whole visual cortex integrating that audio information and working on the audio information.
And I think that's exactly what I'm saying, though, as well with the North Paw and these other things, is that your body quickly adapts and the brain can reroute around. Like when people do go blind, their sense of touch, like the sense of touch of Braille readers, is amazing compared to like you or I. Like you could touch us with something, and we wouldn't know it, but a Braille reader would know a lot more.
So one more thing I wanted to bring up in my podcast is that, when someone does, one result that surprised scientists recently when they do MRI scans was that the brainwave pattern that when someone gets when they're looking at a real apple is different from what they get when they're looking at a virtual apple. And they couldn't figure out why this is. And I think there is an obvious answer to that. So I read this book, and scientists should read this book. It's called Criteria Causation. Actually, it's called The Neural Basis of Free Will, Criteria Causation. I think a lot of people did not read this book because it has the word free will in it. But you should read this book. You especially should read this book because you love neuroscience, and this is a hard neuroscience book. The Neural Basis of Free Will. Peter T.S.E. I don't want to mispronounce his name. He's a brilliant guy. You can watch some of his talks on YouTube. So criteria causation is this. It's the answer to it is the answer to why you look at the way your brain is going to be different when you look at an apple versus when you see a virtual apple. And this is important to neural lace because if we send an apple through the computer and through the neural lace, so we have the brain imaging. Okay. If you know you're getting an image through your neural lace, then the brainwave pattern of an apple you're getting through neural lace should be different from a VR apple, and it should be different from a real apple. And the reason why is because you know it. So it's like, okay, so and this also, I don't know if this is going to be too much for one podcast. So the idea is, from criteria causation, is that your neurons are coincidence detectors. And they're only detecting, like Hebbian learning, they're only detecting when a neuron receives a signal between a certain span of time, which is it's modular. The neuron can adjust. So that could be like 3 milliseconds. If it gets 2 signals within 3 milliseconds, then it activates, right? And so you have this coincidence pattern, and you have a network of coincidence patterns. So let's say that in the brain, when your neuron activates. This is a computational biology idea from the idea that when your action potential fires, it's a 1, and when it doesn't, it's a 0. But let's say that and now we know it's actually more. You can't summarize it so simply. Now we know.
I think it is a little bit more complex than that.
Yeah, it is. But because a neuron has this, the dendrite is itself a computer, and you can't just really like reduce all information to a 1. Besides, the action potential has amplitude, it has a wave, and plus you're really talking about whole networks.
I think part of the problem is beyond such simple signaling.
Yeah.
And if you look into something like quantum like quantum biology,
Sure, yeah.
it throws all this stuff to the wayside in
well-
some way. Not all of it to the wayside, but there are some complex things like quantum tunneling of the mitochondria.
The observer effect. How do you square the observer effect with neural lace? And I do have a proposal for that too.
Yeah, well, I'd like to see it. I mean, I think there's some interesting, ways we might go about, figuring this out. If when you look at like the small brain mammal preservation prize, or like turning the brain to glass, right? They got all the position of the neurons, but they lost all the metadata.
So my thinking is that that a particle is like a polarized wave, and a wave is like the decoherence pattern that you get through the double slit experiment when you observe it is like a depolarized particle. I mean, usually when you talk about polarization at that level, you're talking about, as a particle travels through space, which direction is it pointed at, the electromagnetic wave. But a particle itself could be also considered a kind of polarization. It's a different kind of polarization. So my thinking is, like, what if a particle is like a 1 and the decoherence pattern is like a 0? Okay? And then so when I observe a particle and there's a feedback loop, so this is what I said, is when we communicate, when we have neural lace, is if the brain is like a network, like the internet, is it more like TCP, transmission control protocol, or more like UDP, user datagram protocol? And so with TCP, you actually have to have a connection, a feedback loop to between the 2 points. If we have a connection to what we're observing, then observation and the observer effect is more like TCP. Right? It's not what we intuitively think. It's not just a packet of data thrown at us. We're making connection to what we're observing.
It's a packet signaling something coming back.
Yeah. And so that's why, when we observe something, if it turns from a particle into a wave decoherence pattern, it's like when we're observing something, we're getting the one's coming to our brain, and it's turning into a 0. It's like the 1 is traveling from the universe into our brain. See?
Yeah. So. It's interesting. I mean, there's some weird things with the feedback in the brain. I mean, like I didn't want to interrupt you before, but when you're talking about the VR world being different than that, I have a talk called VR in the Mind.
Yeah.
That basically looks at the neuroscience between virtual world and this world, and what makes you basically embedded into that. What are the properties that make you actually feel like you're in there? Why the reason people fall over when they're in there, and why, part of it has to do with the speed, the size, the color, and if you get these like 4 or 5 different things right, the brain does believe you're in there. But then there's a number of experiments they do where they take, for example, they'll put a heating band on your arm in the real world.
Yep.
And then they'll project a fake arm in the world, and then in the same position though, with another band on it, and they'll change the color of the band.
Yep.
And and they'll ask you, at what temperature does it seem too hot? And so if they have the color as blue, which is traditionally in the brain a signal for cold, the temperature which they feel it's hot is lower. If it's red, the temperature could go higher when it's blue. When it's red, they feel that their arm's burning before it's reached that same temperature.
So how do I know something is hot or cold? Or how do I have the concept of hot or cold? Or how do I have the concept of a cup? Well, in deep learning, a concept, which deep learning is sort of based on neuroscience, a concept of a cup basically is sort of a map of all the links between all the different lines and edges that the computer is seeing that make up the cup, that it's associating with the cup. So it's really a map of associations. Any concept in any domain, whether it's audio concept, whether it's audio-visual concept, where it's like, I see a microphone and I see a tripod and I hear a tripod when I knock on it, and I'm not going to knock on it because I don't want to mess with the microphone. But if you had any kind of concept, all it is a map of the associations between all the different lines and edges and colors or sounds. It's just a map of bits.
Yeah, but that map pulls into like
patterns.
into a pattern. It's like a bucket of ideas. But there's a coffee cup and there's a water cup, and yet one has a handle and one doesn't, but our brain knows they're both a cup.
Right. So the idea is that what I'm seeing on the table, though, is a concept. I'm not seeing anything other than a concept. That's why, let's say the corner of for a human, in the corner of your eye, you don't have the same sort of color vision in the corner, and you only have focus on what you're directly looking at. So what's to the side of your eye is kind of blurred out. But yet you don't experience a table as something that loses color in the sides of your eye or something. What I'm saying, the point is that what we're seeing is a concept of the table. There's all sorts of optical illusions you can see to sort of like, there's actually a hole in your eye, and you can use a pencil at about the length of 6 inches from your eyes to figure out where the hole in your eye is. You're not seeing anything at all with that hole, but you don't notice there's a hole in your eye in your everyday observer thing. So we're not seeing anything except for a concept, and a concept is actually consisting of so let's say that we have in the brain with criteria causation, we have networks of coincidence detectors, or networks of, so a coincidence is a bit, and we have all these bits that are the associations are being mapped until I have the concept of a cup. And this is in my mind, and we're also mapping this with imaging. So this is what we're doing when we see a cup, is we have a map of associations of coincidences. And then what I'm doing is taking this map and capturing it with all these sensors and all this artificial intelligence technology. And then once I have it, once the computer knows that, oh, this is the okay, so back to the apples, just because we're running out of time. So the idea is, why should the brain image of when you see a real apple be different from when you see a virtual apple and when you see an apple with neural lace? And the reason is because an apple is, in some sense, the criterial summation of all the different pieces of criteria that you've put together. So because you're in an MRI machine, and you're in an MRI machine, and you're seeing a virtual reality, the sum total of your experience that you're observing is based on all this criteria, that's based on all the knowledge of everything that's true, and that unique brainwave pattern must be different, in fact, because between whether it's a real apple or virtual reality, because the information that's summing up to that unique brainwave pattern, that neural correlate, has to match that sum of that information has to match the sum of what's true for that situation. So if you're seeing a virtual apple, it should have a different brainwave pattern from seeing a real apple, because it's a different summary of information in your real life, different brainwave signature.
But what about isn't every apple you're going to throw a little different brainwave, like a red apple versus a Granny Smith versus a...
Yes. A Granny Smith, a green apple, and a red apple should have a different neural signature.
Yeah, that's what I wonder about. Honestly, my biggest question is, how are we going to get to like a drilled down level of the information going across into the brain and out of the brain?
Yeah.
Like I use some of these neurofeedback headsets, for example, like a Muse, where I meditate and I can control the weather pattern, and I have a game where we can measure the brain intensity, and I can hover a ball at different levels, and I can move it through an obstacle course, and there's all these things. But I'm ready to. I make a joke that I'm ready to start shaving my head just so I can wear the EEG headset.
Yeah.
But I'm much more at this point. I think there's a lot of stuff that could be done from the outside of the brain, and I think that then we would probably move into the neural lace or something inside the brain that can. I think we should really be really good at reading before we start trying to write. Or like to create, but obviously that's where the big benefit is being. But I think you can also write by, there's these other trainings of brainwaves where they say, like, imagine you're closing a box or you're like opening a box, and then that could correlate to something completely different. And you just trigger that visual fingerprint of electrical activity in your brain, and it can like open and close the door, And so
nice.
I think a lot of it could be basic like that. I mean, I was thinking that you could also use some audio input into the neural lace. Like you could say the thing, or you could at least think the pattern it might go into your brain.
How do we get things into the brain?
So generally there's something called the blood-brain barrier, which is, as it sounds, it's a barrier that stops particles of a certain size or certain shapes or certain class from entering the brain. However, I have seen some recent studies that might allow us to temporarily put down this barrier. There's an ultrasound technology that's using little tiny micro bubbles to basically fire it. If you fire it at this barrier, it puts the barrier down. And so there's going to be a lot of other molecules that maybe had been too big or had otherwise been ruled out.
So I think also that part of the brain is actually below the blood-brain barrier. So we could target, if you like the old brain, if they target the lower part of the limbic system, especially the part coming into the spinal cord area. That's another way to. It's just another option.
If you're trying to hit that like quote unquote croc brain,
Yeah.
and where you have like some of your that's more
In
where
fact,
your
I am.
reactions are and things.
Well,
I think a lot of the neural lace
It's
stuff.
but it's also actually all your incoming senses hit the croc brain first. So that's like the convergence point of all your incoming senses. So it's a key interest for
Yes, but
neurolace.
your thought and your conception of things that are not immediately based
Sure.
in this moment where you're like that's your prefrontal cortex.
Sure.
It's kind of the later parts of your brain to evolve, and where I think a lot of neural lace activity would go.
Well,
So if you're trying to shock me to get up, you want to maybe use something in the cerebral, in the cerebral cortex.
to debate you,
Yeah.
just
Okay.
to debate you on
Yeah.
the topic. My feeling, and which could be wrong, is that if we target the old brain, we can. I want to do VR for the brain, which means VR and AR without glasses. So I really am focused on the old brain because I just want to be able to send an image to you that you interpret as VR or AR. So that's why, I'm into like the sensory areas, the primitive.
That's the
primal
occipital
areas.
nerve. You have basically a whole other area for visual processing.
I'm not interested necessarily in messing with people's high-level thoughts. Not yet. The first product of Neuralace that I'm interested in building will just will be targeting the lower level primal sensory inputs.
That's interesting because I would probably, as a matter of debate, think that the best spot would be to go to the higher levels.
Okay.
Because that might offer you more flexibility in generating images or things to force feedback into the brain.
One other thought on the note of that debate, real quick, is that you could sort of imagine. I imagine the brain as a feedback loop as a whole, as basically a fractal of feedback loops, if you will. So there are grand feedback loops and small feedback loops. So everything comes in through our senses to the thalamus to the old brain, and it goes through the neocortex, which is the new brain, the new rind, and then at the peak of the neocortex, it actually comes back to the old brain, back to the thalamus. It's as if the thalamus is both the entry point of the senses and the top of the pyramid of the neocortex at the same time, because it's a big loop. So that
I understand that, but some of your context of the cup and the apple.
Yeah.
If you read about people who have a stroke,
Sure.
they can't recognize basic objects sometimes.
Well, here's another possibility is if we can just interface the brain at any point, regardless, and we can call different parts of the brain. Basically, if we have the transmission protocol of the brain, which I like to, it maybe has to alternate between the two, like UDP and we'll have sub-authorizations like HTTP, but for the brain. And once you have that communication protocol, if you have a brain port, no matter where you're connecting to the brain, you should be able to request any other information from any part of the brain.
I don't know that it works. Have you ever heard of the colostrum?
Of course, yeah. The colostrum, yes.
So colostrum was Francis Crick of
Right.
Crick and Watson. He was working on that until he died. I recently became very interested in it. It might be another topic for one of my talks, but he basically posthumously had published a paper on the colostrum. He was working on that until the day he died.
Yeah.
He really believed he found the center where consciousness exists in the human brain. Whether or not you believe that, I mean, there is some evidence that it actually plays a role integrating information from all the different areas and could in turn actually be related to generating consciousness. So I don't know, think we even know the real target point of where we want to enter the brain. I think if we want to have the neural lace be able to lift your arm up,
Sure.
we might want to hit deeper in there. But if we want to imagine a spaceship floating on the table, then we're going to want to hit the higher level parts of the brain.
Great to debate with you. These are all great ideas. Definitely, it's not really, our debate is pointing to the fact that there is no secret sauce for solving neurolace. We can talk about neuroscience all day long, but you're not gonna get the magic trick from a single podcast or a podcast series. It's just too much information.
I think we're early enough along in the neural lace race.
Right.
The neural lace, which could turn to a portmanteau, but basically, no one knows how it's going to be solved yet. I think there's
Sure.
some leads and some hunches.
But what we can say is that we can see that there are things that we can do that have never been done before, and we're going to do them.
Yeah,
Yeah.
I mean, I definitely, I'm bullish. I think that we'll reach some level where it doesn't make sense to be
I'm talking about applying self-driving car type technology, artificial intelligence, computer vision. All this stuff hasn't been done yet. Why not? Let's do it.
Well, Mike, I hope you do it. 'Cause I would love a neural lace. Let me know.
All right, cool. All right, thanks, man.